Hi, everyone. Yeah, very happy to have Stephen Heilman today from USC, who's going to tell us about stability of three-candidate plurality. Thanks.
All right. So thanks very much. And so thanks for the invitation. Also, since it's being recorded, I'll say I make a lot of mistakes. And today should probably be no exception. And please feel free to interrupt me if you have questions or something is unclear, especially in this online format. You know, it's good to interrupt me. Otherwise, I'll just keep going. Anyway, so here's our main question for today. Given votes for candidates in some election, which election method best preserves the winner of the election if some of those votes have been corrupted or miscounted? So I guess this is also probably an analysis seminar. So I could say our main question for today is some analysis of Boolean functions. You could say also motivate things like that. But anyway, so what do I mean by election method and why would this question be interesting? Well, if we remember in 2000 in Florida, there were something like 537 votes that determined who the president of the US was. So it's fairly likely that a small number of votes affects the outcome of the election. It seems like our method for choosing the president, the Electoral College, does not seem to be the best at preserving the election's outcome if some of the votes get messed up. So maybe I won't dwell too much on the Electoral College, but yeah, in this particular presidential election, there was about 500,000 more popular votes for Gore, but nevertheless, just due to the way the Electoral College works, it's like a weighted, it's sort of like a weighted majority vote, where each state is weighted a different way. And like I said, I won't dwell on this too much, but yeah, it's just the way that it works that Florida ended up being the tipping point in that particular election. Okay, so eventually I'll be more precise about what I mean by a voting method and what I mean by a vote. So I'm just starting with a little informal introduction. But thinking about different voting methods and the mathematical questions behind them really goes back at, say, 200 years at least to Condorcet, and then with some game theorists, there was a lot of activity in the 50s and 60s, and then some renewed interest in the math and computer science community in the 90s. And I always like to put up this table which shows different voting methods. So each row here is going to be each row here is going to be a different voting method, and each column is a desirable property to have. And so you can see, say, let's look at the fourth row. The instant IRV stands for instant runoff voting. You see there are many green entries in the fourth row, so it has many desirable properties, but there's also many red entries, so there's many properties that instant runoff voting does not have that are desirable. And you can see any particular row, it's not all green, it has some reds. So kind of the lesson from this table for me is there's no perfect voting method. Like today, I'm going to talk about one property of voting method. I'm going to say, oh, this majority or plurality is the best for this particular property, which would correspond to like looking at one column of this table. But the overall lesson is there's just no best voting method, because you can make an argument for one being better than the other just by looking at different properties. Okay. Okay, now I'll be a little more mathematically precise. So I'm just going to talk about voting methods with two candidates to get started. So suppose we have some election with two candidates. I'll label those candidates as 1 and -1, and we'll have n voters. And each of these people are going to vote for either 1 or -1, and I'm going to tabulate the votes. So I'm going to say xi is 1 if person I votes for candidate 1. And I'll say xi is -1 if person I votes for candidate -1. So I'll take all those -1 and 1s, I'll put them in a vector, call it x. So x is just a list of all the votes, if you'd like. And so what is a voting method? It's just a Boolean function. Its input is the x, the set of votes, and its output is either -1 or 1. So its output is the winner of the election. Any questions so far? Like I said, feel free to interrupt me. So just, the general idea is you can think of a Boolean function as a voting method, that's all. Okay, now let me try to be more precise about the main question. How do we find the voting method that's most stable to corruption in the votes? I'll be more precise about what I mean by corruption. So just like before, we have a Boolean function, and I'm going to fix a parameter rho between 0 and 1. And we'll start out with x. It's just uniformly distributed in all n length vectors of -1s and 1s. And then given that x, I'm going to define a random y, which is basically going to be the same as x, just correlated with it. So all entries of y are going to be independent, and for any particular ith entry of y, so flip a coin. So with probability rho, I'll keep yi equal to xi, and with probability 1 minus rho, I'll resample the ith entry of y so that it'll be uniform in -1, 1. Okay. An equivalent way of saying that is yi equals xi with probability 1 plus rho over 2, and y equals minus xi with the remaining probability 1 minus rho over 2. And so if you just do your little calculation, x and y really are rho correlated, so their correlation. Well, I just wrote their covariance is rho, but we have -1, 1 valued things, so it's the same as correlation. Okay, so this is our main question. So we're thinking of the x. Maybe I'll try to annotate a little on here. So the x, I'll do this on the next page. Main question is we have our original votes x, the x of the original votes. We compare that to, and we look at f of x, so that's the winner of the election with the original votes, and then we compare that to f of y, so y are the corrupted votes. We're comparing f of x, the winner of the original election, to f of y, which is the winner of the corrupted election. And so this is our main question. Let's fix our rho. We want to maximize this probability. We want to maximize the probability that the original and the corrupted outcomes are the same over all functions f. Okay, so I just copied that main question up there. So is the question clear? Can anybody tell me how to maximize this quantity? I guess you don't want to have your answer recorded on video.
If f equals constant, I guess.
Yeah, exactly. So the way I phrase this question is easy. You just take f to be constant, right? We're asking to maximize a probability, and if f is constant, then the left side, f of x and f of y, will always be the same. So this probability will be 1, and that's certainly the highest it can be, right? So I intentionally stated this question so the answer is easy, and it's sort of a silly answer, yeah? So in order to get some sort of non-trivial statement of maximizing this probability, we're going to add some extra assumptions. And so from the election perspective, this f, this would be like, whatever the votes are, I ignore them and I just declare candidate 1 wins, right? Which is sort of an uninteresting election method. Okay, so here's an extra assumption. So we're going to maximize the same probability, but overall Boolean functions, but we're going to add the constraint that the average value of f is 0. So for half of possible votes, candidate 1 wins, and half of all other possible votes, the other candidate wins. So for this question, it's a little, the way I phrased it is not quite as obvious, but answering this question where we add the constraint that each candidate has an equal chance of winning, that's also easy. You could take something, any function that looks like this, that depends on one coordinate in this way. So fx is x1, for example. This will maximize the above probability. So in voting terminology, this f that I just wrote, you would call it a dictator function. This corresponds to ignoring all the votes except for the first person to vote. For that reason, we call this a dictator function. Okay, but once again, this is, since this question is sort of easy and its voting interpretation is not so democratic, we're going to add an extra assumption to this question. So we're going to add an extra assumption that will eliminate the previous example of a dictator function. So we're going to assume what I have written here. I have all of the partial derivatives of f are small. So this will eliminate the previous example of a dictator function. So once again, this is an analysis seminar. So this is basically assuming that the L2 norm of each partial derivative of f is small. And when you add that assumption, this question becomes harder. We can interpret this, so making all partial derivatives small, we can interpret that as every voter has a small influence on the election's outcome. So it turns out the answer to this main question now is, so what is the best function there? It's the majority function. And that's not as easy to prove.
How small in this result influence?
Yeah. Okay, so you're asking for the precise statement, so I'll skip to the precise statement. So it's this.
Okay, I'm sorry, I didn't want you to skip. Please continue.
Oh, you didn't want to skip. Okay, so well, here I just copied the same statement so as before. So this is the real precise statement. So I fix my correlation parameter rho. I fix an epsilon bigger than 0. Then there exists a tau such that if I have a Boolean function whose mean value is 0 and all of its partial derivatives are smaller than tau, then this probability of preserving the election's outcome is less than or equal to the optimal value plus epsilon. So yeah, I don't think I'll try to annotate this. This quantity here is, let's see if I can write it in text. That's the limit as n goes to infinity. We can get that there. Yeah, so this quantity written here, it's the limit as n goes to infinity of this probability, the quantity on the left when f is the majority function.
Sorry, Steve, there's a question in the chat about L2 norm. Why is it the useful norm here?
So as opposed to like an LP norm or something. Yeah, you know, this function is -1 valued. So if I take L2 norm or LP norm, I guess you know, these differences, they're going to be either, you know, 0s or 2s, and then I divide by 2 squared. So I'm taking the maximum. Oh, fair enough. Yeah, so since these differences only take 2 possible values, then I guess taking the LP norm or L2 norm doesn't really matter, I guess. Yeah, thanks for the question. Any other questions? Yes, but I guess the bigger question is why did I use, if I could sort of read into that question, you're saying, why am I using L2 norm when, from what I just said, switching to a different LP norm doesn't really make a difference? Well, you can actually make a similar statement here in the majority of Stablest theorem where I cross out, you can actually cross out this -1 and change it to just real valued. You have to change a few other constraints, but then in this case, having the L2 norm here is sort of the most natural thing to have. Maybe that's, once again, trying to read into that question. So that's the bigger answer to the question is there is a way to write this in a more general case. I didn't do that here, but in this more general case, having the L2 norm there is most natural. But thanks for the question. Any other questions?
You say there exists tau. Is it known what is tau, or They just
Oh
say.
yeah. So.
Or it depends on epsilon or.
Yeah, and but the main dependence, I guess, is on the row, if I remember correctly.
Oh, okay.
Yeah, but I guess it would have to. Yeah, I think it should depend on both. But yeah, I think relatively sharp estimates on the tau are known, I think. Once again, I'm sort of skipping some details here, but yeah, good question. Any other questions? All right, so this is a nice theorem. It has some other applications. Its main motivation was actually to computer science, but maybe I won't talk about that too much today. One key property, though, is that it holds for any n. So this is, in some sense, a dimension-independent statement, if you think of n as the dimension.
Stephen, one more question.
Sure.
I think on the previous slide you had sum over all derivatives, right? And here you have maximal. Okay. I'm sorry.
Yeah, it's fine. Yeah. Sorry if it was unclear, but yeah, it was just I said all of them are small, and then I did change notation. Instead of saying all of them are small, I changed notation to the maximum. Fair enough.
Okay, thank you.
Okay, so this is sort of all there is. Well, it's not all there is, but this is sort of the big statement about the Boolean functions, or that is, thinking about elections between two candidates. But especially from the voting perspective and for computer science motivation reasons, we want to have the same sort of question answered for 3 or more candidates. So we want the same sort of question to be answered, for more general than just Boolean functions, say, when your domain is like 3 points to the n, something like that. And that's it's still an open problem. So this would be called the Plurality of Stablest conjecture from, I guess, about 2004 or 2005. So that's what I'm going to talk a little about today. And so once again, skipping over a lot of work of a lot of really nice work of a lot of really nice people. So back in these pluralities, in the majority of Stablest theorem, we have this correlation parameter rho. And the way that their proof works for any rho, any correlation. It turns out when this correlation is close to 1, so a lot of people, most notably Milman and Niemann, so that's a typo actually. So Milman, Niemann, 2018, more or less solved this problem in the case where rho. Yeah, let's just cross that out. Sorry to Elkanon, but they more or less solved this problem when rho equals 1. That is, so I haven't stated what the problem is yet, right? But they basically showed when the correlation parameter is equal to 1 in some sense, then plurality is the most stable voting method. And I worked on that a little bit too. But this, I'll also emphasize, this built on a lot of work that a priori maybe didn't seem related. Most notably, I'll say Colding-Minakazi, they did this really nice work on mean curvature flows and asking sort of what singularities occur in mean curvature flow. And this was a really nice paper in 2012. And the so-called double bubble problem which was solved in 2004. So there's a lot of nice work that's been done related to this problem, just in the case where this correlation parameter rho is equal to 1.
But Steven, can I ask one more question?
Sure.
If rho equals 1, it just means that y always equals x, right?
Yeah, exactly. So yeah, you're seeing through my lies. So yeah, thanks for thanks.
Just, right.
So what I really mean is that rho is the correlation tends to 1. So let me try to draw a picture. So say if I'm looking at like the maximum noise stability, so I'll just abbreviate that as like NS. as a function of rho. Sorry if this is sort of sloppy. And then I look at rho near 1, then as you're saying, you understand what the value is at the endpoint, rho equals 1, but it turns out as the correlation goes to 1, the derivative of this noise stability can be interpreted in terms of surface area, and in particular Gaussian surface area, in the limit as n goes to infinity. So does that answer your question?
Yes.
Okay. Yeah, so once again, thanks for picking apart my lies. Yeah, there are some additional details here about this correlation tending to 1. Okay, so sort of a lot of work we sort of understand well what happens when this correlation parameter tends to 1. And so this new work, which I forgot to mention at the intro, but this is joint with my graduate student Alex Tarter, who's also at USC. So we basically showed that plurality is the most stable voting method for 3 candidates when this correlation parameter is small and positive. So it's sort of the first result of this kind. Okay, now, like I said, I wasn't really precise about what question I'm even asking, so let me now try to be more precise. I'm just going to restate some of the definitions from before, for where I started with 2 candidates. Now let's talk about 3 candidates. So we have 3 candidates, 1, 2, 3. Our voting method now, it's a function with domain 1, 2, 3 to the n, and it takes the values in 1, 2, 3. As before, we have our correlation parameter rho, and the x, capital X, uniformly distributed in 1, 2, 3 to the n. We interpret that as like every possible vote that could happen among 3 candidates. And just like before, given the x, we define our y so that all its entries are independent. And I'll make the same definition as before. So we flip a coin with probability rho. We keep the ith vote the same, so yi equals xi. And with remaining probability 1 minus rho, we'll resample yi, so it'll be uniform in 1, 2, 3. Okay, so just like before, x are the original votes, and y are the corrupted votes. And same question, we want to maximize the probability that fx equals fy. As we remember from before, we need to add some extra assumptions. So let's see. So just, this is an analogous to before. I assume the probability that fx equals I is, say, 1/3 for all i's. Just assume that's possible or something. Then same sort of conjecture as before. The maximum of this probability, so the probability that the original winner of the election is equal to the corrupted winner of the election. The maximum of this quantity over all f's where each candidate has an equal chance of winning, and such that all partial derivatives of the function are small. That maximum occurs when f is the plurality function. Okay? This is the conjecture. We don't know that it's true, but this is the conjecture. And so just to be clear, what do I mean by plurality function? I mean f of x is equal to the candidate with the most votes when the votes are x. I just copied the conjecture up here. And like I said, new result for today is, okay, so this constant dependence is really bad, but at least it's some constant that I can say what it is. So conjecture holds when the correlation parameter rho is smaller than whatever that number is. Some really small number, but at least I can say what it is. Okay. So the proof, as in the works that I mentioned a few slides ago, uses calculus of variations in a way that does not depend on the ambient dimension n. In fact, the the result that we get, it doesn't just say something about free candidates, it's a corollary of a more general theorem. So here I just rewrote the plurality of stablest conjecture for any number of m candidates. So whereas before I just had functions from 1 to 3 to n, now I just changed 3 to m. So this is really the real main theorem, that if your function f maximizes, like is the solution of this conjecture, so it is the function that maximizes the probability that fx equals fy, then f is m-1 dimensional in the sense that it's a function of m-1 chunks of votes. So rather than being sort of an arbitrary, function rather than being some sort of arbitrary function of whatever the xi's are, it's really just a function of m-1 chunks of votes. So that's sort of a lot to comprehend. Just think of the case m equals 2. When m equals 2, this structure theorem says that whatever the most stable voting method is, 2 candidates, it's going to be a function of just the sum of the votes. We know that the majority function is a function of the sum of the votes, but so right, the structure theorem doesn't just all the way solve the problem, but it sort of almost does, right? Because it sort of reduces what possible functions you could be looking at to this very specific class. Any questions? Okay, so I just copied that theorem. Here I just want to say more or less this new theorem combined with an old result from when I was a graduate student, which was dimension dependent. So when I was a graduate student, I basically I gave a dimension dependent statement of solving this plurality stablest problem. But this new structure theorem says, well, if you have a dimension dependent result, it becomes dimension independent. So basically old result plus new result equals the 3 candidate plurality of stablest for small correlations. Once again, skipping over some details here, but this is just the kind of idea. Oh, I think did something just pop up in chat? So you only look at votes for candidate 1 in the first subset, votes for candidate 2 in the second subset. Yes, I think that's what I had written there. Oh, yes. Any other questions? Yeah, so the details of what numbers are appearing here aren't so important, but the main gist is that, just like I said before, instead of the universe of all possible weird functions, you can just reduce to thinking about functions of chunks of votes. Okay, there's also an analogous result when rho is negative, but maybe I'll skip talking about that because that actually gets a little more complicated. Okay, so let's see, so we're about 30 minutes in. So plan for the rest of the talk is I just want to sketch a proof of this structure theorem for 2 candidates or 2 sets. So the first step, which I won't talk about too much, is this so-called invariance principle. So there's a way to start with the discrete question that we had and change it into a continuous question, so a question about subsets of Euclidean space. And that's sort of a whole story in and of itself. Once again, that gets back to this so-called invariance principle stuff. So the idea there is, if I have a Boolean function, once again, we're returning back to Boolean functions, so you can forget about having more than 2 points in the domain. So if I have a Boolean function, I can write f as a multilinear polynomial. Probably most people know that, I guess. Then, if I write it as a multilinear polynomial, I can consider if I consider it as a multilinear polynomial, then I can extend its domain to all of Euclidean space. And in particular, I can think about the set of x's in Euclidean space where fx equals 1, for example. That's kind of the idea. Once again, I'm skipping details here, but there's just sort of a general way of starting with a Boolean function, sort of extending it to all of Euclidean space. Maybe I actually should have said bigger than or equal to 0 instead of equal to 1. But anyway, there's a way to do this sort of transference, I guess, if you want to call it. And so sort of taking that as given, that we can sort of make an equivalent statement from the discrete setting to the continuous setting. Now I'll just talk about the continuous setting. So the continuous setting, we know that when you have -1 ones that are uniform, you expect some sort of Gaussian maybe in the limit, and that's certainly the case here. So when I have so I'm changing settings now. So I have a function f in Euclidean space. I'll let gamma n be the Gaussian density. And for any rho, I'll define the Ornstein-Uhlenbeck operator applied to f in the usual way. So hopefully people have seen this before, I guess. If not, that's fine. So if you haven't seen this before, you can think about this as the sort of the heat operator with the Gaussian version as opposed to the Euclidean version. It's like running a heat equation, but like a Gaussian version of the heat equation. And then for any subset A of Euclidean space, I'll define its noise stability like this. So I'm integrating indicator A times T row indicator A. So T row indicator A, that's like running your, I'll draw a picture on the next slide, but you basically have, maybe I'll just, on the right, in the right figure, I have indicator A, and then the slightly lighter gray line is like evolving indicator A with a heat flow for a little bit of time. Right, so you start out with indicator A, and then it sort of smooths it out. All right. Backtrack, sorry. I have indicator A, and then I multiply by T row indicator A, and then I integrate with respect to the Gaussian. So if you'd like, you could call this quantity, which we call noise stability. You can think of it as Gaussian heat content, maybe. Especially if people come from a more analysis sort of background, you could think of, what is heat content? It's like the same thing, but the heat operator instead of the Ornstein-Uhlenbeck operator. So we can think of this as Gaussian heat content of a set. So the analog of, so the continuous analog of the majority of Stablest problem is Borell's theorem, which I'm stating right now. So suppose we have a set in Euclidean space now, and we have a set B that's a half space, and A and B have the same Gaussian measure. Then the noise stability of B is bigger than or equal to the noise stability of A. And so, I'm sorry, let me clear that. I just copied the statement from the previous page, and I'm drawing what I mean by a half space. It's everything on one side of a hyperplane. So another way of stating Borell's theorem is that a half space holds its heat in the most. Okay? Or sort of holds its heat in the best. And once again, this is sort of the continuous version of, I'll write that down, so go in one ear out the other. So this is a continuous version of the majority of Stablest problem. Okay. So once again, I didn't go into the details, but there is a way of making an equivalence between our discrete statement about those Boolean functions and this Borell's theorem that's on the screen now. And this is the picture I showed before. So let me clear this out. Okay. So like I said, the plan for the rest of the talk is to give a variational proof of this Borell's theorem. We have several proofs of this theorem, but I haven't seen a variational proof of it before. So here's how we can do it. First step, what do you do? First thing you do in calculus of variations, you do first variation. So it's like taking a first derivative. And so what do you get here? You're going to see that whatever set A, I'll just backtrack to it. We want to show that the half space has the largest noise stability. Okay. Supposing we had a set that maximizes noise stability, it would satisfy this equation that we wrote here. This A is equal to a super level set of the Ornstein-Uhlenbeck operator applied to indicator A. That's just what you get from first variation. That is taking a first derivative. So it's like taking a first derivative with respect to sort of squishing your surface in a small region or something like that. So here's a pictorial demonstration of what's meant by this. So we start out with indicator A. Start with the indicator A, then we evolve it according to some heat flow. So it's sort of smoothing out the set. Then there's going to be some constant where the super level set of this, we're going to take the T indicator, we're going to take a super level set of it, and we're going to get back to the same set that we started with. This is what the first variation condition tells you. So in this picture, that's probably not going to be true actually, but just the cartoon version is saying that it's supposed to be true. Okay. So that's step one. In fact, yeah, it's sort of a separate question, which I don't actually know the answer to, but I'm thinking that's what sets A satisfy this equality? Sort of a question in and of itself. It's not really clear why. So when you start thinking about this question, you're like, well, okay, this should really be pretty rare for sets to satisfy this. That you sort of start with a set, you evolve heat, take a super level set, and get the exact same set as you had at the start. But it's sort of hard to characterize them actually, in general, at least as far as I can tell. Anyway, that's a side question. So anyway, that's our first variation condition. Knowing that we have that first variation condition, what happens when you take a gradient? So we know from calculus 3, if we have this T row indicator A, when we take a gradient, and we take the negative of that I'm talking about the quantity that I have here. If I take the negative of the gradient and then I divide by its length, it's going to be the unit exterior normal to the set A. So I'm just using like calculus 3 stuff, right? The gradient is always perpendicular to the level sets, but A is its own level set. So if I multiply by -1 and normalize, I can get the unit exterior normal vector by just taking the gradient of this quantity. Okay, so that's realization number 2. Once again, we haven't really used anything fancy. I just rearrange things from the previous slide. Okay, I'm going to be intentionally imprecise here a bit. Let's go back to the definition of well, I guess I wrote it here already. By definition of the Ornstein-Uhlenbeck operator T rho, and the chain rule, if I take, so I'm talking about this line here. If I take the gradient applied to Ornstein-Uhlenbeck, I move the gradient inside, I'll get this gradient indicator A. You can make this precise, but easier to explain it by being a little imprecise. We know gradient indicator A is basically like the normal vector. And with chain rule, we're going to get a row here as well, and a negative. Okay. So once again, I'm being imprecise, but we understand if you know distributions and stuff, you know that you can make this precise. Still haven't done anything fancy. Now we're just going to combine all the above stuff. So kind of unclear why I'm doing this, but I'm going to start with this quantity. By equation 2, so equation 2, if I just substitute it into there, I have normal vector n times length of the gradient is equal to minus the gradient. So that's how I got this quantity here. And yeah, then equation 3 here, I'm substituting equation 3 into this equality here. So I'll get this weird looking identity between V inner product normal vector and sort of the average of V inner product normal vector. So that's the key identity. So I'll just copy that on the next page. Hopefully I'm not, if that was a little confusing, I'll just say nothing too complicated goes into proving this identity, but this is sort of the key identity that the average of the normal vectors, that's the thing on the right, is sort of equal to the, up to multiplying by the right thing, it's equal to the normal vector. That's probably worth writing down. I'll skip it. But I'll just say it again. Average of the normal vectors is equal to the normal vector. Oh, and by the way, V is fixed. I guess I said that at the top. V is a fixed vector. Okay, I'm going to skip a few. So when you do this variational argument, so I have the key identity still above. When you do this variational argument, everything boils down to this. So this is the key thing. You want to look at, whoops. You want to look at the second derivative, this thing. The second derivative of this noise stability as we do a translation of the set. So we're starting with our set, call it A, and we have our vector V. And we're just considering what happens if we take that A and we translate it in a direction V. That's all. How does the noise stability change as we take the set and translate it in the direction V? And we take a second derivative. This is a standard thing in these sorts of arguments, that everything sort of boils down to taking the second derivative. Okay, and then you see something cool happens when you do this second derivative calculation. I'm gonna, on the one hand, as I sort of highlighted in the colors, I'm gonna get the average of the normal vectors. That's the quantity that we had from the right side of the key identity. And the other quantity that appears is exactly this blue thing, the quantity that appeared on the left side of the key identity. So somehow some magic happens, and when you take the second derivative, you get two terms that are, according to the key identity, they're more or less the same. How are they different though? They're not exactly the same. You get this factor rho here. So you sort of put everything together. As we said, we had two terms that were the same. So when we combine them, we're going to end up with this quantity that's left over times something that looks non-negative. But remember, this rho is between 0 and 1. So this 1 over rho minus 1, that's going to be positive. Okay, now we need to think for a second. So remember, we're maximizing noise stability. If we have a maximum, then its second derivative should be non-positive. Second derivative non-positive, but we showed a non-positive thing is equal to something non-negative. Right? Having a maximum is what it means to be a maximum. That your second derivative is non-negative. On the other hand, we showed it's equal to something non-negative. Therefore, this whole thing must be equal to 0. And then, so some initial, you can basically show the first quantity. It requires an argument that's not too hard. The first quantity is not 0, therefore, the second quantity must be equal to 0. Therefore, as we wrote here, the second quantity must be equal to 0. I skipped this detail here, but this means that Vn, so V is fixed, n is the normal vector. This must be 0 for any x. That means that your set A is one-dimensional. That's it. So see, it didn't really use anything too complicated, I guess. So that's the variational proof of this inequality. And the key fact is that this proof works for any number of sets. So here's the corresponding statement for any number of sets. If we have a bunch of sets, A1 to AN, that are disjoint, so if I just draw a picture, so we have like A1, sorry for the mediocre drawings, but if like sets A1, A2, A3, for example, if we want them to maximize the sum of their noise stabilities, then they're going to be low dimensional in this sense. They're going to be low dimensional sets cross R, cross R, cross R, cross R. And this is the real main theorem. Okay, I think that's about all I wanted to say. So thanks for listening, and I'll take questions if there are any. Thanks.
Thank you, Stephen, for the great talk. Yeah, please ask any questions you might have.
I have a question.
Sure.
So I have seen this proof of Borell's theorem. There is a function of two variables, very strange function. And there is some kind of Jensen's inequality Gaussian version. You can think about this integral of indicator function times t rho of indicator function as so probability that the standard Gaussian belongs to A and the rho correlated Gaussian belongs to. And there is this proof, which I think it's a semigroup proof. I think the first proof that it was a little bit difficult, and this simplified version, I think, is due to Niemann, Mosse, I guess, Mosse-Niemann, I guess. Mm-hmm. So for plurality stablest conjecture, is there some kind of it's for two sets, but for many sets, how would you state that question?
Yeah, so I guess the bigger question is, does their method apply in this case? Is that what you're saying?
Yes.
Yeah, as far as I can tell, no. I think probably both of us have tried separately. I mean, I can't say what other people have done, but I'm pretty sure we've all tried that and it hasn't worked so far. That doesn't mean it won't work at any time, but so the quick way of saying is I have not been able to get it to work that way.
Okay.
Yeah, I'd like to, because I agree, it's a very sort of aesthetically pleasing proof method, but yeah, I haven't gotten it to work.
Okay, thank you. Thanks for the very nice talk.
Yeah, and so, but the bigger answer to what you're asking is, so you can take this perspective of sort of trying to do a heat flow sort of proof, but there's sort of a change in perspective in a lot of recent works, not just of me, but of other people, that we shouldn't necessarily think of like heat flow as in like evolving some sets and looking at them like some quantity that decreases. We're sort of thinking instead, we'll assume you already made it to the minimum or the maximum, then tell me properties of the sets that are there. You know what I mean? It's sort of like a little bit of a change of perspective. But yeah, anyway.
Okay.
Any other questions?
I was just curious, this obstruction m equals 3, it comes from your earlier result, as you mentioned, or?
Yeah, exactly. So let me go back. Yeah, so the question is, why can I only do 3?
Yeah.
And the answer is, so I think I wrote it here. So new result says if you prove a dimension dependent result, it immediately becomes dimension independent. The old result only worked in the case of 3 sets. So all that we need to do is to do to solve this problem, say in 3 dimensions, when this correlation parameter is small, something like that. I think it actually should be possible to do that, but not in a sort of interesting way, I guess. So yeah, really. So in principle, the real answer to your question is, in principle, it should work. Sort of the same sort of proofs. So the case when I was a graduate student, that 3 set case, it really should work for a larger number of sets. Though there will be some additional difficulties which are of a bit technical nature. So if your bigger question is why, really, what is the issue there? It's I can just explain actually pretty quickly. So you have some free space. So let's say I want to maximize the length sum equals 1 to 4 of the lengths of the Gaussian moments of these AIs squared, where say each of the AIs has Gaussian measure 1/4, and they're a partition. Okay, so if technically this problem is not solved, and you could even just solve it in three dimensions. If you could solve this problem in 3 dimensions, then I could. This is the main technical issue to solving the problem for 4 sets, and replace 4 with any other positive integer. That's the main technical issue. So I think that answers your question.
Yep, thanks. Any other questions?
I saw such extremal problem in some work of Naor. Can you maybe say a connection?
Yes, exactly. So that'll be code Naor. So that's closely related, not exactly the same. So the problem they have is the same problem. Switch to green here. They have the same problem, but then they have no measure constraint.
Mm-hmm.
But yeah, it's almost exactly the same problem without the metric constraint, but they're closely related. So the non-constrained and the constrained problems are very closely related, obviously.
Mhm.
Yeah, and even that problem without the metric constraint still not solved. But and similar statement, if you could solve it, then this is one main technical hurdle to dealing with the plurality stablest problem.
Mhm.
But yeah, thanks for the question.
Can I also ask one more quick question? When
Sure.
m is strictly greater than 2, what's the continuous version of this plurality stablest theorem?
It's exactly the one that I was on the previous pages. It'll be this. Without saying, yeah.
So, but what's the difference? This is your theorem, which is proved, but you said you eventually managed, when rho is small, perhaps because going to the Hamming cube, right? There is.
So yeah, the discrete version was, as you said, the plurality stablest. This is the continuous version. Sorry, maybe I'm not understanding.
But you said that you eventually proved plurality stablest for very small rows, right?
Yes, when m is 3.
Yes, when m is 3, let's say.
So
where does this smallness arise if this is continuous version and if some
okay, so yeah, another good question. I'll just warn you, I have to teach soon, so I'll probably have to leave soon, but so I can connect this to what I just drew. So when rho is small, we know from Fourier analysis that this is basically constant plus the sum of the Gaussian moments, maybe times rho plus some of the Gaussian moments, AIs squared, plus say big O rho squared. So this is the connection between the two. So when rho is small, this big O rho squared term is negligible. And the main term is exactly the sum of the Gaussian moments squared. That's why, that's the connection between what I was just talking about and this current case. And that's why I need rho to be small in order to make the method work, because I use that connection.
Mm-hmm.